Oh hi, today the main topic is B-tree, the part 2. The last video I just recalled what is B-tree and why do we have to learn about it and what's the background of it. So why even is being used. Because this thing is really practical. It's not really some kind of theory, it's really being used in the software industry. So now we're just gonna make it advanced. Why we have to think about performance, time, complexity, and those kind of things. Why we just can't just insert without caring about time complexity. So we normally put index file on the disk. Why? Rather than putting in the RAM is the volatile, the memory. So if you try to turn off this computer, this RAM is gonna be gone. But this is non-volatile memory. So if you're trying to turn off your computer, it's gonna be there's gonna be alive. The database has to be alive, even though you turn off the server. I mean, like it's like of course. So it has to store in the disk, but disk is kind of slower than like the memory thing. But I'm just gonna try to explain more about like more easily and more definite and more deep. So, but why is it slow? Why? Let's just try to explain the kind of operating system or computer architecture of it. What is program? The program. So what is the program? So program is kind of really the bunch of instructions. There's some instructions, and this is of course a program. So this instruction is actually made by assembly code. But when you're trying to click it, so it's gonna be running, right? So when it can be runs, that's called the process. The process is also called as the running instance of the program. Program is the process. Okay, that's pretty good. When we're trying to run this program, the CPU has to be triggered. I just said the program is just there's a bunch of instructions and the computer is the one who reads the instruction and execute it. And this kind of thing is very simplified. There's more about it. Example, there's instructions. And let's say there are A, B, C instructions here. The computer can really execute this kind of instruction A and B at the same time. Why? We know there's some kind of concurrency and those kind of thing in the computer, but actually it isn't. It seems like we're doing the same thing, so we just make it on just like simpler term of it, but there's no doing it at the same time. What do you mean by that? Even if you look at our world right now, if you're trying, example, you watch some kind of F1 race, and when the two cars, when they looks like going to the same time in the end line, but if you look closely, if you look at the milliseconds of it, there should be difference, and there's no same time, like in the world right now. But in the computer world, it's all the same. But why there's concurrency about like of computer architecture, computer industry? It's actually because of the CPU scheduling algorithm, because that is switching so fast and it just seems like doing it the same time, but there's no same time in this world. Let's go here. So I just talk about there's no same time. The computer can execute the A, B instruction at the same time. So what we have to do is, let's say we have a bunch of 1,000 instructions. Computer have to memorize this. So rather than putting this as a variable, it's stored in the memory of it. So based on this kind of, there's actually the bytecode of this kind of instruction, because assembly there's like already bytecode of some kind of this kind of assembly code. So but whatever. So there's a bytecode of here. Using this bytecode and the memory here, it has to make a unique address and put it into memory here. And when you're trying to insert this kind of instruction here, instruction A, B, C is gonna be stored in here. So the computer has to be fetch this kind of instructions and decode and execute, because it's gonna be encode also making also like really smaller, or making it to bytecode, right? So if you're trying to the CPU, there are a bunch of instructions, and the processor puts this instruction into memory, and it doing fetch, which is getting instructions to execute from the memory, and it decodes it, it converts into the CPU friendly code, and it executes it. So execute is the running. So, but it's doing the other thing also. Example, when you're trying doing fetch, decode, and execute, and also B has to be go with the fetch, decode, execute by time. And moreover, if you look at the x86 architecture, rather than making this as a fetch, decode, execute like this kind of through way, and make this other instruction to wait, it puts like the similar to the not similar to the concurrency. It's just like making thing is not being in the idle state. So when the A is instruction is being fetched or it's already decoded, put into when it's being decoded and fetch here, and when you fetch it go to the queue, it's called a prefetch queue. Put it to B here. So A is being already decoded and executed, and next is C here and D in here. If it's done, you go B, C, D, E, those kind of things. So how do we really guess this kind of A, B, C, the next memory address? We can just increase the program counter, which is the it's just the really kind of some kind of like register value for tracking which instruction has to fetch. So PC is also known as program counter. There's already a register for it in the CPU. The register means kind of like some kind of storage in the CPU, but there's a many purpose of it. The general purpose and special purpose. The general purpose is kind of like being used for the just like as a storage, like a variable, but special purpose is this kind of PC for the special purpose. But rather, so those kind of things is really complicated, and this kind of really complicated but abstract is kind of fast, right? Because moreover, when you're trying to look at it, how this worked, there's actually some kind of the how to say it, the way of it. So because this is actually part of the process. The process and the memory is actually separated. But there's the link that the wire that link into this kind of memory, which is also called the bus. There's a memory. There's a data bus. There's a address bus, and there's the control signal bus. But whatever, it's kind of really kind of like the highway. Example, the first highway. If you have experience about the driving, the first highway is for the speed, right? But second highway is for the small car, and third highway is for the large, like big car, like the truck. So there's a purpose of the highway, like here, but also this kind of the bus is kind of similar way. The data bus is for the but data, and the address for bus is for the address. Control signal bus is the one which is for the control signals. So example, you're doing the fetch, right? Fetch. That means that you have to send the memory address, because you have to find find some kind of this kind of value, but you have to know about this kind of memory orders, right? In this moment, the address bus is gonna be used. And also you have to send the control signal bus. What you have to do is, it means that I want to do something, but there's kind of already abstract and rules of these signal. Example, I want to read some kind of memory. I want to write into some kind of memory, right? The control signal is meaning for that. There's a read and read write and whatever stuff. And let's say we just have to read from the memory. You don't have to read by this kind of value, right? You just have to get this value. So control signal bus is gonna read. The data is when you're trying to fetch this kind of instruction, you have to send it back to the CPU, right? So those kind of thing is actually it's kind of like link of it, the wire link, and that's gonna be also data bus, because the instructions, the bytecode is the data. So those kind of thing is really abstract and fast, but the disk is actually out of this kind of boundary. So this is kind of reason that disk is kind of slower than memory, but also because there's kind of a cache in the CPU to like communicate with the memory. But disk is like there's also a cache of it, but it's kind of far here. Even in the hardware, there's a hardware specification of the memory and the disk, but I believe that the memory is also faster than the disk. Also, there's a hardware spec moment, and there's even the not software moment, like those kind of fetch cycle thing. So those kind of thing make the disk operation read like the write or reads like slower than the memory. So we just found out that even though it is ON, but if we're using the memory, it's kind of pretty fine. But if it's like this, it's way slower. So we just found out that our indexing database in this algorithm should be fast because we're not storing the memory. So I think this is it. So it's kind of really open system computer architecture concept that why fetching the data or the database is slow. Why do we have some kind of like the fancy algorithm B3 or B+3? This is why we should make some kind of search algorithm even faster for the database. Also, this is actually the kind of the last content I'm just gonna talk about, which is the limitation of the bit tree. The bit tree is pretty fine for the single operation, right? Because it's log Tn, right? The time complexity. But if it's like range, like search 100 to 100, like 10,000, it's gonna be kind of slow, because let's say it's k here. It means that all log t and the time complexity is k. So this is kind of like the problem of the bit tree, and I think that is why I believe there's kind of B+3 to reduce those kind of range operation. And I think there's also BP8 or something. So, well, whatever stuff. So this is the Have a nice day. See you next time. Bye bye.